Okay, so we've already seen all the hardware of the MP1, so we're now going to have a look at the embedded software that's available for the MP1. So there's quite a bit of information to get through here in this set of slides. So we're going to have a look at the embedded software distribution components. We're going to have a look at that demo launcher you saw in the first hands-on to show you how it uses all these software components. ST mainlining, so ST's been mainlining all our drivers, so I'll show you more information about that. I have a slide from the third parties, which I think you've already seen from the marketing presentation, so I'll have a bit more detail about that. Then we'll have a look at the distribution delivery, so the items that make up the whole of the distributed package that you download as the SDK. Licensing terms, so always worth remembering that it's all software, so there is licensing rules and regulations. Most are open, but some of them aren't, so you need to understand all the licensing terms. And then the wiki itself, so we keep mentioning the wiki. I'll show you a bit more detail about what's on the wiki and the type of information you're going to find on the wiki. So the software components. So we have the two components. So we have the part that looks after the Cortex-A, which is the open ST Linux distribution, and we have the part that looks after the Cortex-M, which is the Cube and all the related ecosystem that has been around for the STM32 family for many, many years. So on the Cortex-A side, you have the two contexts, so you have the secure context and the non-secure context. Each of them are completely separate. You boot usually through the secure side first and then launch the non-secure side. Again, it will depend on what you're doing in your application, how you use each of those contexts during the actual application. We do phrase it as open ST Linux distribution. This isn't customized. It's just our way so that you know it is the one that's got all the extra drivers inside for the MP1 device, but they're all open drivers. So everything's out there in the community. You can download any of those drivers. So even though we've called it Open ST Linux, it's not being customized at all. So what do we have inside the architecture? So at the top, you've got your trusted applications, which are running in your secure context. And then you've got your general Linux applications which are running in the non-secure context. So each of those applications you write, and they will then talk to the open ST Linux distribution, which is all connected to the framework and the board support package. So there's two different modules that make up that. As I said, even though we call it open ST Linux, we've mainlined 95% now of our code or drivers or anything that's related to the product. So it's all out there in the community. The few remaining 5% are either to do with debug or security or the graphics module, as you'll see, which isn't ST's IP block. So that 5% is small, everything else is out there available for you. To build our distribution, we've used community tools, so we're using the Yocto community tools to do our building of our distribution package. And the solution has also been adopted by Linaro as well. So for the secure side, we're using the Linaro devices. So if we have a look inside the distribution package, we have in the application framework, so underneath your trusted application, we have the secure monitor and opti, which is the running of the trusted application execution. And then you've got the normal Linux middleware in the user space, which will be running all the open sourced Linux applications like ALSA, GStreamer, Wayland Western for graphics, things like that. Each of these application frameworks will then talk to something in the open ST Linux board support package. So in the case of the secure side, it'll be coming up from the trusted firmware, which is the first stage bootloader and the boot chain to launch that. And in the general or non-secure side, your second stage bootloader, so U-boot, will be then launching your Linux kernel and all the drivers that are part of the Linux kernel so that you can run your Linux middleware applications. And then on the side of that, you have the coprocessor or the Cortex-M4. This is completely separate to your Linux side, and this is everything that you've ever generated with the STM32 Cube. You can still use operating systems in this side, so things like FreeRTOS can be used to run whatever application you want to run on the Cortex-M side. So the OpenST Linux distribution components. So what do we have? So this is a breakdown of a generic driver. So you will have your Linux application, which you will be writing or you'll be sourcing from wherever. That will be communicating into the Linux middlewares or the submodules, which are generic applications to do various tasks like the graphics, the audio, the modem, comms, things like that. All of that happens in your user space. Then these Linux middlewares will talk to the kernel space and the framework that goes with each of those drivers. Some drivers will have sub-frameworks as well. And again, these frameworks are all generic community-based drivers. And they will then physically go and talk to the ST hardware, which has the driver that's provided by ST, which is what we've mainlined on the community. So we've opened up the access to all our drivers. And in the case of graphics, the green box here on the bottom right is the GC Nano. So it's the graphics driver. It's not an ST block. We've purchased it in. So that one is a third-party block. So it's not actually controlled by ST. So if you now look at all the peripheral drivers, so you can see the free context at the bottom. So over on the far left-hand side, we have the secure context, where you've got OptiCore running, secure monitor, things like that. And up in the user space at the top left, you've got your trusted applications talking to that. Then in the large section in the middle, you've got your non-secure, so your Cortex-A non-secure, where your general Linux applications will be calling all the general middleware blocks, and they will be then going into the kernel space, calling the various items to do things. So TTY, which will then call the USART driver for your communications interface. Suspend will be calling some of the power and reset drivers. USB host will be talking to the USB peripherals. RP rock will be doing all the messaging system so that you can talk to the coprocessor. So all of these drivers will have an ST component, which is driving the hardware, and it'll have a community component which is providing the interface between the Linux middlewares and the ST physical hardware. Then finally on the right hand side you will have your real-time applications running on your Cortex-M. They can be using FreeRTOS if you choose to, you don't have to. Then you've got all the ST middlewares that you'd have used in the past, so if your real-time application needs to use USB, so the ST USB drivers will be used. Open amps in there so that you can communicate with the Cortex A side, and then you'll all have the standard HAL drivers that if you've played with STM32 before, you should be familiar with the hardware abstract layer that we use for all of the STM32 devices. So if we move to the top side of that diagram now, so this is now the Linux middlewares, which sits between all those kernel drivers you saw earlier on the previous slide, and your Linux application, which is right at the top. So here you now have all the community-based drivers like Whale and Western for graphical interfaces, GStreamer for doing the GUI, ALSA for your audio, a few of the other ones are in there. So GDB Server for doing debug, Python for doing some core, Bash, things like that. So they're all standard applications that you've got in there, which are all Yocto compatible and Open Embedded compatible. So again, you're using standard drivers, but this is all part of the Open ST Linux distribution. So they're all standard drivers that we've taken. For the IP block that's not ST's IP, so it's the GC Nano, so it's the Vivanti graphical driver that we have inside the MP1. It's done by VeriSilicon, so it's a third party that we've used, it's not ST. And all the libraries are provided in the OpenST Linux distribution. Source code is available, but you will have to sign an NDA directly with VeriSilicon to get the source code. If not, you will use binaries inside the OpenST Linux distribution. And this library pack can do OpenGL ES 1.1 and 2.0 and OpenVG 1.1 as well. So you can get the source code in the kernel space, but in the user space, if you want the source code, you have to sign that NDA. As I said, there's no charge, you just need to sign the NDA. For the Cortex-M side of the MP1, so the Cortex-M4, Here you've got no restrictions. You can fully reuse any STM32 MCU code you've written for Cortex-M4 using the HAL. All of that can be reused. So the hardware abstraction layer or low layer peripheral drivers are exactly the same. If you use the middleware components like the USB, the free RTOS, lightweight IP, FAT-FS, you can use all that. When you install STM32 Cube, you've got hundreds of examples to show you how to use different peripherals in different ways. And all of that code and examples that we produce is always going through a continual quality cycle. So we're always checking, getting feedback from customers for errors, fixing them, republishing it back on the internet so that you can download again. And all our STM32 Cortex-M4 type software is business friendly licensed. So you don't have to worry about any of the licenses and reusing any of that code as a starting point for part of your application. So if we look at what you get within the Cortex-M world, so you've got your legacy framework from all STM32 devices. You have the HAL or the low layer APIs talking directly to the hardware. You have those middleware components I mentioned, so lightweight IP, free RTOS, communicating either to the HAL or those low layer drivers. If you've got add-on shields like the X-Nucleos, so you've got the Arduino connectors on the bottom of the board, you can use any of the board support drivers that we've written for them. So most of our devices have got board support packages. So if you're using a MEMS sensor, you'll want the driver for that MEMS sensor to communicate through SPI or something like that. So all of those softwares available. And then your existing user code will be talking through a defined set of instructions or APIs. So any user code you've written can all be reused again inside the Cortex-MP1. So you've already had a look at the demo launcher. So this is what we saw first thing this morning. So this is the default software that should come inside the board. Here we've got an inbuilt application where you press on each of the icons, so the camera preview you saw demonstrated earlier, the AI, the 3D cube, the Bluetooth speaker and that. Each of these applications uses a slightly different set of frameworks, be it user space frameworks, kernel space frameworks, to talk to the different parts of the hardware needed to do the demonstration. So we have our graphical display. Our application to display that is calling the DreamStreamer application, which is calling the Whalen Western drivers. That's talking down into the kernel space to talk to the graphics element, to use the graphics processor. And it's also then driving the hardware, be it HDMI or the DSi display as well, to give you the image that you're seeing on the display. When you run the video, you get some audio. So that's then calling the ALSA plugin, which is then using the various frameworks. So you've got the ALSA framework, then the sub-framework that goes with that, which is then calling the codec driver to go and talk to the audio codec and playing the audio out either through the headphone jack or through a connected Bluetooth speaker. So you can see the flow there of what's going on inside the standard video playback part of the application. If we look at the AI application, so this is the one where we're using the Cortex-M side as well. So we have our AI application running on our display, which is asking you to enter a character. So you then use the touchscreen, which is in the bottom. Touchscreen is then communicating through an I2C driver, through a kernel space driver called TSC, so touchscreen controller driver, into the application. It's then using the GStreamer and Whalen Western and the graphics driver to display on the screen the character that you have just drawn on the touchpad. As well as displaying that driver on the screen, the application is then also using remote message to send that link with the information it's received over the IPCC and the MCU RAM. So it stores the information in the MCU RAM, communicates to the Cortex-M core through the IPCC. Then on the Cortex-M side, the IPCC will signify to the Cortex-M core we've got a message. The OpenAMP application, which is the community application, will then take that message from the MCU RAM through the virtual HAL UART into the application, which is the AI application running on the Cortex-M, to do the analysis to decide exactly what character you have just drawn on the screen. Once it's decided, it'll then send the message back through the virtual HAL UART, the OpenAMP, write the information into the MCU RAM, tell the IPCC to notify the Cortex A side that we have information. That'll come back up through the remote messaging back into the AI application running on the Cortex A side to decide exactly what action you're now going to take based on the character that the AI Cortex-M side has decided it has just received from the touchscreen panel. So mainlining. So what do we mean by mainlining? ST has been working in the backgrounds now for the last 3 to 4 years with this MP1 device. So we are over in the bottom left hand corner with a new silicon and a new board, and we've been writing our drivers. So we've been upstreaming those drivers into the community for people to check the quality, the rules, regulations of an open source driver. They've then been feeding that information back to us as ST, and we've been modifying our drivers and then going around that loop until everybody's happy. ST's happy and the community's happy that all the rules and regulations have been followed and we're not generating any spurious errors into code that we've generated. So the Linux community has been working on that with us over the last 3 to 4 years. Then you've got what goes on in the bottom right hand corner, which is we've got known silicon and we're launching a new board. So when we're launching our discovery board that you're playing with today, we will then have to potentially modify some of those drivers to use the additional components that are on the main discovery boards or the eval board. And again, we go through that loop of modifying the drivers, letting the Linux community sort it out, make sure we've followed all the rules, regulations, and then we go around that loop for a while until everybody's happy and all our drivers are robust, they're not going to cause any crashes. Everybody's tested things multiple times on different versions of hardware, eval boards, things like that, to make sure there's no errors. So all the information that you're downloading from the community is reliable, it's been well tested, and it's not going to cause you any major issues for using it. So that's what mainlining is. It's us as ST uploading it and working with the Linux community to make sure everything's there and working correctly. So advantages for you as a customer. So it means because we've tested it all, the quality's there. So lots of people, it's not just us as ST testing it, lots of people out in the community have already done tests on it. So we know that there's a lot of quality control going on with running this particular process. So it means it reduces a lot of risks for you because you know you're not the first person to come and test this particular driver. Someone else has probably tested it in that way 2 or 3 times out in the community. Also, because we're following all these rules and regulations, when we transition from one version of kernel to another and you change different platforms and port stuff, scalability is always there. So again, you know that the transition from one version to a newer version or updating a driver from an old project to a newer project means that it's fairly seamless, the process, because again, everybody's out there been doing all of this before. And because you're not having to write all the software from scratch, there is a cost incentive to this. So it makes good sense for you because you're relying on all these well-tested drivers, giving you portability, and you're not having to sit down and write them all yourselves. So there's a big cost incentive for you. So this mainlining process has a lot of benefits for you as a customer. So how do we manage the different deliveries? So we're currently over on the top left, so we're currently on kernel 4.19 today. That will run for the next 12 months, where we will keep doing software updates, evolutions, fixes, and modifications. At the end of that 12 months, we will then launch the newer core, so we'll move on to the next kernel release. But from that point, we'll then stop doing any evolutions on kernel 4.19, but we'll keep doing fixes. So we'll keep maintaining that existing kernel for at least another 12 months. With the new kernel, we will then go back to doing the same thing. So we'll be doing evolutions and fixes for that new kernel for the first 12 months, and then for the second 12 months of the newer kernel, we'll then potentially upgrade kernels again, and we'll carry on with just doing fixes on that previous kernel. So this is, I think, is a standard Linux time frame diagram that you will see. It's 1 year of evolution and fixes, then 1 year of fixes, and then you'll migrate to a slightly newer kernel, and again the process will start again. For support, inside ST, we have the R&D team who've been developing all this and generating all these drivers and then mainlining them. So they're all there. Level 2 support is what we call our competence centres. So in the case of Europe, it's based here in Prague, and they've got specialised people who will talk to the R&D people if they find any issues and resolve the issue for you, the customer, on the far left-hand side. Sitting between those two support centres and the designers, you've got the ST community, so it's all the web forums and online support, and you've got people like myself, the FAEs, who are there visiting you, dropping in to see how things are going and helping you getting your code up and running. To get access to either the FAE team or the community, you either go through the forums to get into the community, or you enter the tickets through the online support system. So they're all web-based processes. You've also got, fairly small here on the diagram, the partners. So sat between the customer requests and the collaborative spaces, there are lots of ST partners out there that are certified who may be able to help you based on specific sections of code that you're using, things like that. And the partners are feeding directly into the ST communities and sorting out issues for us and compatibility problems, things like that. And for downloading information, we've also got the GitHub as well. So in the collaborative spaces, you can pull different drivers and that down from the GitHub. So inside ST, as I say, is all the items in the blue, and then outside you've got all the community items and the third-party support people there. So the ecosystem, so we've already seen this from the marketing slides earlier today. As well as what ST is generating, there are lots of, as I say, partners out there generating different things. So we've got people doing trainings, engineering services, embedded software, so you've got Crank for graphics, you've got hardware tools, software tools, so Kyle, AC6. And then if you choose not to design with a chip level solution yourself, you can then go to some of our component and module manufacturers. They're all partners with us, where you can get the DRAM, the micro, the power management on a little module. You then attach that to your board and then you build the rest of your design. So you don't have to worry about the high speed layouts parts and that. So as I say, there's lots of different partners out there, all doing different things. We have our partner services description link there on the website. So you can click on that link on the slide and it'll jump you off to the web page to go and see what partners are out there and what they do and their exact services. You saw earlier we've got different distribution packages. We have 3 different packages available. They all come together, but they're different available. So the starter package, which is what you have running in your discovery board, it's really there for evaluation purposes, for you to play around. The development package, that's when you really want to develop your own applications, modify the kernel, board support, items like that. And then when you've done all the developing and that, then you'll want to release your own distribution package. So you'll then go through all customizing what you're going to release as part of your distribution package. So the starter package is designed for evaluation, so you can run scripts on there like Bash, Python. You can download binaries either through scopy or USB keys, which we'll be doing during the day. And it's got an ST Western image. So that's our image that we've used, which is a Western Whaling image doing the graphics. It's got the default secure bootloader as the first stage bootloader, then U-boot as the second stage bootloader, and that's all part of our starter package. The developer package, this is where you do most of your work when you want to write applications. So you'll be able to develop any application you want using the developer package. You'll be able to play around with the device trees, so you can change what peripherals are in use on a target board. If you want your boot chain to be optimized or different, you can play around with that. If you want to do more secure elements, you can start adding more for the Opti side, and you can even start modifying the kernel itself if that's what you need to do in your application. So everything's in there. We provide all the images as binaries. We've got all the make files available and all the source code for the modules that we're using for the kernel, the U-boot, and the Cube M4 side, so the Cortex-M side. And then when you want to generate your distribution package, we have that one, so we have a distribution package. It's all done with Yocto in the case of us, so we've run all the Yocto tools on it. You can run whatever bitbake and all the Yocto recipes that you need to do to generate your end application and the distribution package. So your distribution package will then generate a nice new developers package and a nice new starter package for you when you run that. So we're not going to tell you much about Yocto, but we provide two different Yocto layers. We've got one that supports all the different boards that we've got for the MP1s, and then we've got one that actually supports the actual device itself. So you've got the items that are common to all boards, the board support package, and then things that are specific to boards, like the eval's got a bigger display, it's got extra peripherals, it's got more connectors on it, and then you've got the actual Linux applications as well itself, so the OpenST Linux applications. So we've already provided all of these for the Yocto system, so if you've got your Yocto tools, then it should be fairly straightforward for you to generate your distribution package. Licensing terms. Each of the different elements of code will have a slightly different licensing rules and regulations and restrictions on what you can do with it. The GNU.org is a great place to go and have a look for some of the more open licensing information, but most of what we as ST provide will be under the BSD type licenses, so you can use it without constraints. There are certain items that are GPL v2. The ones you probably want to be more avoiding is probably GPL v3s. And this is where you may have to provide your entire source code to the community if someone wanted to request it. So you have to pay attention to the different licenses for each of the different software modules you're intending on pulling into your application. So our general application is SLA048. It's a standard license that we have. All of our components, as I say, are fairly easy to work with. The one that's probably more proprietary with the GC Nano. As I say, it is open source, but if you want the source code for that one, you just have to sign an NDA with VeriSilicon. The Bluetooth and the Wi-Fi, they're a module from Cypress, so they will be able to generate, they can provide you with a source code for that, but again, it's a separate license. Most of the drivers, as I say, we provide is under BSD level 2, or GPL version 2, sorry, or BSD. But as I say, some items are on V3. Most of those are to do with debug features and things like that. So you just got to pay attention to what you're bundling inside your package, and is it going to require a license. So for the licensing, you can get more information on the Wiki. So there's lots of, there's actually a full dedicated section for licensing. As I highlighted, the Wi-Fi Bluetooth one, it's not ours, so it's a Murata module based on Cypress, but it is fully open source. You just got to see what the licensing agreements are with that one. And mainly it's the graphics one you have to pay attention to, so the video for that side of things. But all the other codecs are open source and it's all part of the OpenST Linux. So the Wiki, so we keep mentioning this Wiki, we keep giving you links to different pages. So here's a few shots of what actually the Wiki is. So here we've got the main landing page, wiki.st.com. You've got your main headers, which is the welcome, the reading tips, the getting started guide. For what you'll be using most, it'll be in the development zone. So the development zone, obviously you've got things about the embedded software, the tools, the device itself. Getting started is where you select which board you're on, and it gives you a quick up and running with the getting started. Development zone has got a lot more information, obviously the prerequisites that you need for your environment, your host environment. You can see release notes about the ecosystem, the OpenST Linux package, any of the Cube programmer packages that you might need to program the device. you can get all the information that we've just seen on the slides about the starter package, developer package, distribution package, more detail about what you can and can't do in each of those different packages. You can have a look into the embedded softwares for either the Cube side or the Open ST Linux side. So again, you've got both sides in there. You can drop down into the Open ST Linux distribution, have a look at the different layers and images that we've got. You can drop down all the way into the drivers, so the framework drivers, the user space drivers, the actual physical hardware drivers for the HAL or the low layer. All the other different components that make up the embedded software, so there's links for those. You can go into the operating system itself, so you can actually go and have a look at the things like the analog and have a look at the different subsystems that we've got into the Linux operating system. And then you can even dive straight into, say, an I2C overview of what parts are doing what in either the user space or the kernel space and things like that, and have a look at the API descriptions for each of those I2C commands as that slide is showing there. Same again with the middlewares, so it's the outer overview there, so you can have a look at even the middlewares rather than the specific drivers as well. Then finally, when you get round to doing trace and debug, there's a chapter on that inside the wiki as well, so you can have a look at the debugging tools, the monitoring tools and different tracing tools, how to debug for TFA, how to debug for U-boot, how to debug for Opti, GDB server commands, things like that. So you've got lots of information inside here in the wiki. So what actually do we have again? Just to summarise for the embedded software section. We've made code generation easy, so all the drivers have been mainlined. You can download them from the web. As I said, we call it Open ST Linux. It's not customised. Everything is being pulled directly from the web based on information that we've already sent up to the web. Again, because it's mainlined, you can ensure that the quality is there. You know that there's a community out there that's doing all the testing of our drivers that we're doing. You can implement things fairly easy. If something updates, you can migrate across really easily. If you're playing around with the Cortex-M4 side, any of the code that you've previously done on another project for M4 can be reused inside there. And when it comes to building your whole application, we're using community tools like Yocto and that to actually generate the actual distribution packages. So you can see that there's lots out there that can make your life fairly easy and fairly fast to get started with the STM32MP1.